Welcome back. Today we'll talk about simple harmonic motion, which is a very special kind of a thing, and all periodic and aperiodic motions can be expressed in terms of simple harmonic motion of a fundamental frequency and harmonics thereof. That is, the frequency is nu, then the harmonics are 2 nu, 3 nu, 4 nu, 5 nu, like that. Okay. These are the possibilities, and that was in the analysis of what is known as the French Fourier, mathematician Fourier. Okay, in the 18th century, he came out with a beautiful mathematical description. Well, as I told you, that the key word is disturbance, and disturbance in this case is from an equilibrium position. At the equilibrium position, for example, if I have this thing, a straight line motion about this equilibrium position, these are the ends, and there is a motion to and fro between these 2 points. And so on this side, if I say that the amplitude plus A, and this side it is minus A, this is the maximum disturbance that is there, we'll talk about that. It simply means that we have things like that. So anyway, the displacement x, we are taking in direction x, we could take y, we could take z, we could take a general r, no problem. That is a function of time t. Okay. Now, the basic of description of simple harmonic motion is the force is equal to minus kx. This is according to what we have the spring, and therefore k is the spring constant, r is a constant, is a positive constant. Okay. So f is equal to m d2x upon dt2, so I can write that here, and I repeat minus kx, so I can write this equation, which is the equation for the acceleration. And the acceleration, you can see it is equal to minus k upon m, both of them are constants, both of them are positive, into x, which means that the acceleration, there is a negative sign, and this negative sign is very important. If x is away, then d2x upon dt2, which is the acceleration, is always trying to seek the equilibrium position, is always towards the equilibrium position. It opposes that disturbance, and we get minus k upon mx. So I can write this d2x upon dt2 is equal to omega square x. Okay, where omega is equal to k upon m, so that omega becomes equal to under root k over m. Omega is equal to 2 pi nu, as you know. This is the angular frequency, and this is the frequency. So I can write from here that 2 pi nu is equal to under root k upon m, or nu is equal to 1 upon 2 pi under root k over m. Now we know that the frequency nu is related to the time period capital T by this relation, and therefore I can write the time period of oscillation in the simple harmonic motion of any kind, of any variety, as T is equal to 2 pi under root m upon k, is the opposite. Okay. Now, we see that from these relations, and particularly in this relation, what is that? That the second order time derivative d2x upon dt2, which we also write as x double dot, okay, this is equal to minus omega square x, which means this is proportional to the function itself. Okay, then we search in mathematics. In mathematics, when we search that, we have a sine function, a cosine function, and e to the power of plus jt and e to plus j theta and e to the power of minus j theta, which we leave till I tell you about the phasors in the case of the electrical alternating circuits. Anyway, and I tell you about the phasors, etc. Right now, with our search, I find that I propose that let there be a solution x is equal to a cos of theta. Well, x is equal to a cos of theta, and theta, well, this is the reference circuit. This is the reference circuit where the theta is generated. Initially at time t is equal to 0, the angle over here is phi, and finally at time t, any time t, it becomes equal to omega t plus phi, where I'll tell you what is omega is the angular frequency and phi is called the initial phase. What is it called? Initial phase. Okay, I'll have occasion to talk to you about that more. So if I take this simply as a cos of theta, okay, then I can write dx upon d theta, the differential of x with theta, as a into minus sine theta, a into minus sine of theta. Okay, well, that is how the books do. I don't do that. I told you in the last lecture and in the beginning that this is equal to dx upon d theta is equal to a cos of theta plus pi by 2, okay, which I'll explain over here. But if I differentiate it again, then I get d2x upon d theta 2 is equal to minus a, again sine theta is differentiated cos theta. Okay, so you find that because this is equal to something and this will become equal to minus x. Okay, now let us take the second this thing, a cos of omega t plus phi, and take the d dt or x dot. Dx dt will become equal to a is a constant, and then we have for cosine omega t plus phi, I get minus sine of omega t plus phi, and when I differentiate this argument of sine, then I get omega plus 0 because phi is a constant. Okay, and similarly when we further it, then d2x upon dt2 turns out to be equal to a, for sine I get cosine, okay, cosine function, and when I differentiate this again, so that I get omega plus 0, so this omega multiplies with the existing omega and I get this equal to minus a omega square cos of omega t plus phi, okay, and which I can write naturally as minus omega square x, okay, or I can say that what we proposed, what we defined, that d2x upon dt2 is proportional to x itself. So what I get is that the double differentiated time function is proportional to the function itself. Of course there is negative sign, of course there is some this thing. Okay, now by my method, which I explained to you earlier in lecture number 4, 5 somewhere, okay, you can search that, I can write it by my method that x dot is equal to dx upon dt is equal to a omega. Now I wrote it as cos of omega t plus phi, so I can write it. Omega will come out here after I differentiate this with respect to time, so I get it here. The argument or the phase becomes equal to omega t plus phi plus pi, which means that this cosine function is the same function as this cosine function. Okay. So the nature of the function is not changed in my method, and now I can compare easily the phase of this with the phase of this. The phase of this is equal to omega t plus phi by 2 minus omega t plus phi gives us pi by 2. So that means this, the velocity leads, the velocity you know that it's given somewhere over here. Okay, so we can show that the velocity leads the displacement by pi by 2 radians. When I go for the second differential, then d2x upon dt2, which I write as x double dot, this becomes equal to a omega square cos of omega t plus phi plus pi by 2 plus pi by 2. I told you there that every time I differentiate that, my phase increases by pi by 2. So we've done it twice, so it will go increase by pi by 2 plus pi by 2. Now, anyway, you know that, or you can show that with the help of the compounding, that cos of theta plus pi by 2 is equal to minus cos theta, and sine of theta plus pi, that is plus pi by 2 is equal to minus sine of theta. Okay, so here I get, I am not writing that negative sign over here, but my phase will tell us here that it will be pi radians ahead of it, and therefore that is why we say that any time the acceleration is leading it, in the first case it is the displacement, the direction of the displacement is like this, the direction of the velocity has been shown like this, and the direction of the acceleration as it appears over here is towards the mean position, and in this case it is towards the center, so we call it centripetal kind of an acceleration. And thus we, in my method, which you may have little difficulty to understand because it's not given in the books, okay, so but once you practice that, you are able to say, now I can say here that the phase over here or the total angle over here, the argument of the cosine here is omega t plus phi plus pi by 2 plus pi by 2. When I compare with this, I find that this one leads this one by pi by 2 radians. So that we can have, I can make it for you that if I have this, then I have this. Okay, so this is the displacement, this is the velocity, and this one is the acceleration, and the velocity and displacement and acceleration, they oppose each other. I will tell you the same thing when I propose another solution for it. Not x is equal to a cos of theta or a cos of omega t plus phi, but instead I will take x is equal to b sine of theta or b sine of omega t plus phi. Okay, in the ensuing. So our proposed solution was x is equal to a cos of omega t plus phi, and which I could write as, okay, when we differentiate it twice, d2x upon dt2, the acceleration is equal to minus a omega square cos of omega t plus phi, which is equal to minus omega square x, which shows that the acceleration is proportional to the displacement and is always opposite to the displacement, that is towards the mean position of equilibrium. Now let us have another proposal. Okay, let the proposed solution be x is equal to b sine of omega t plus phi. If so, then I differentiate it once with respect to time. I will get, okay, for sine function I will get a cosine function. and in the argument it will turn out to be equal to omega will come out, okay. And next time when we differentiate again, then cosine becomes a minus sine function, sine of omega t plus phi, and so I write minus b omega square sine of omega t plus phi, and that becomes equal to minus omega square x, okay, as it was. So this is the solution. By my method, which I proposed to you and told you in the last one, in differentiation what we do is that the function is taken as such. The only change is in the argument or the phase, and that enhances by pi over 2 radians. In the double dot situation, there is another pi by 2 which is added, so to this thing it's total pi, and for pi we write it minus b omega square sine of omega t plus phi, which is again equal to minus omega square x. Okay, the same thing. So by the normal method and by my method, both the cases we get minus omega square x. So this is one of the proposals, and this is another proposals, and we find that both the proposals fit, and we can check that, right? Now, for mathematical consistency, it is said that if there are two solutions separately, then their sum and difference should also be a solution. Let's check. Now, let's put overall phi is equal to 0. When phi is equal to 0, then the first solution is a cos of omega t, and the other solution is a b sine of omega t plus and minus. First, let us take plus. Now, let us do a small jugglery and put a is equal to a star cos of delta, okay, where delta is a constant. A star is also a constant, and b is equal to a star sine of delta. So when I substitute these values for a and b respectively, what I get? A star cos of omega t into cos of delta, plus I am taking only plus sign, plus proposal, a star sine of omega t sine of delta. Okay. Now, when I take a star out, what I get? I get here cos of omega t cos of delta, sine of omega t sine of delta. Now, cos of a plus minus b, as I told you before, and in the last lecture also, is equal to this. One must remember, cos of a cos of b minus sine of a sine of b. Okay, and if, of course, if this is negative, when this is negative, sorry, my okay. And minus sign over here, then I get a plus sign here. Okay, a plus sign over here. Anyway, so what I find is that we get x is equal to a star cos of omega t minus delta. Okay, and if the minus sign is taken, then of course what we get is a minus here. So cos a star taken as common, cos omega t cos delta, sine omega t sine delta. And from this relation, what we get is that cos of a cos of b plus sine of a sine of b gives cos of a minus b. Okay, so we obtain the result for this one. Okay, and that is all I have to do is I have to change the minus sign to a plus sign. Okay, so therefore now we get two solutions. X is equal to a star cos of omega t minus delta and cos of omega t plus delta. Okay. Now let us check. Check by differentiating this with time, and I get x dot, which is dx dt, which is velocity, is equal to minus omega a star. For cosine I get minus sign, so I'll get it sine of omega t minus delta over here. And if I differentiate it another time with respect to time, then I'll get minus omega square a star cos of omega t minus minus delta r, in case it is plus sign, is plus delta, which is equal to minus omega square x, which shows that our friend x double dot, which is acceleration, here is proportional to the displacement. So this is the crux of the matter, and in the next slide I will show to you that instead of taking a star cos of delta as a, and I can take this as a star sine of delta, okay, and a star cos of delta, okay, here, and when we substitute in these results, we'll obtain a solution where I can propose it to be x is equal to a star, or any value is constant, no matter what it is, sine of omega t plus minus delta. I'm going to do it very quickly for you, okay, and explain that. So the proposed solution that we had earlier was x is equal to a cos of omega t plus 5, and from where we got this result and could show that this is one of the equations. Now let us take phi is equal to 0 like before, and proposed solution I write it as it was, a cos of omega t plus minus b sine of omega t. Now what you are going to do here is that let a be equal to a naught sine of alpha. The alpha is another constant, and b is equal to a naught cos of alpha, okay, which can be shown over here, right? The value of alpha, I am just taking it. Well, if I substitute these values, the proposed values of a naught sine of alpha and a naught cos of alpha, then I get this equation as, okay, a naught cos of omega t plus sine into sine of alpha plus minus a naught sine of omega t plus minus cos of alpha. And if I take a naught as a common factor, then we get cos of omega t sine of alpha plus minus sine of omega t cos of alpha, which is just like the compound function here, sine of a plus minus b is equal to sine a cos b plus minus cos a sine b, okay. From that we can write back that this is equal to a naught sine of omega t plus alpha, okay. Now let's check if this is a solution. So when I go from x to x dot and differentiate with respect to t, so I get a naught cos of omega t plus minus alpha, because sine of omega t, sine will become cosine upon differentiation multiplied by omega, and x double dot, which is the acceleration, is equal to minus a naught omega square sine of omega t plus minus alpha, which I can write as a naught this is equal to x, so this is equal to minus omega square x. So the acceleration is proportional to the displacement itself, is opposite to the displacement, always opposes the displacement, and is always toward the mean position, okay. Here again we find that in both the cases that A star square is equal to A square plus B square. So I can write this A star is equal to under root of A square plus B square. And similarly in the second proposal I can take this as equal to A square plus B square, and therefore A naught is also equal to A square plus B square. Tangent of delta is B upon A, and here tangent of alpha is A upon B. You have to be little careful from these relations. So now I have 4 solutions. This is the solution. This set of cosine function, some constant which we call the amplitude. This and this we call amplitude. This is the displacement. Okay. Omega is the angular velocity, so you'll get the, I have already told you about that, and this delta or alpha or whatever you want to write, this is the, when t is equal to 0, the argument of the sine over here and the argument of cosine over here, they become plus minus delta and plus minus alpha respectively. Okay. So this way we have arrived at a few solutions, proposed solutions of simple harmonic motion. Also I told you that e to the power of j theta and e to the power of minus j theta, they are also, where e is the Euler function, exponential, they are also there, and j is equal to under root minus 1. We will have occasion to talk about that. So far in today's outing I have been able to describe the simple harmonic motion, or in terms of a harmonic oscillator, okay, which may have these, any one of these 4 equations. They are satisfying it equally well. It's our choice, your choice, whatever you want, you can write the solution. Now, in the offing is how this simple harmonic motion can be presented in terms of a time graph. And the time graph which shows the to and fro motion, which shows the oscillatory motion with time, that is also obtained from this reference circle. So look at the reference circle, look at theta is proportional to t, and if we differentiate that, we'll get, and then integrate, then we'll get theta to be equal to omega t plus phi. Okay. Please look into the things. If you can ask me a question, why did you take this phi is equal to 0? No problem. I can take any value. I can continue to the value of phi. All that will be there is that a phi will be added over here, a phi will be added over here, and phi is a constant, plus minus alpha or phi minus plus or plus minus delta, of course, is a sum or difference of 2 constants. So you can say that this is another constant, so there is no problem. Okay, whatever way you like, you have the freedom, like you have a freedom of questioning, so you have a freedom of expression also, that you can express your sine function. And remember, try to search for the word Fourier, the name of a mathematician who shaped the simple harmonic functions, simple harmonic values, and he could describe any kind of periodic motion, also aperiodic motion, in terms of a set of sine and cosine functions. This is how it happens. So any kind of periodic motion, repetitive motion, which means that if we have a function of t, this at a time t, the function is equal to t plus n times, any n times capital T, where capital T is the time period, and so this corresponds to, in the omega t pattern, it is 2 pi, okay. This angle, if it is sine function or cosine function, so you can see that sine of 2 pi plus sine of 2 pi plus theta, or cosine of 2 pi plus theta is equal to sine theta or cos theta respectively. So this part also you must check in one of my initial lectures, okay, and the last lecture also gave some idea about it, and I promise I'll repeat it again, okay, in the next lecture when I'm talking about the time diagrams of the simple harmonic motion. Thank you.